Hello esteemed viewers, in this tutorial we will continue from tutorial 2 and from where we left. In tutorial 2 we discussed or we clearly explained the concept of bending moment and shear forces in beams, specifically with reference to simply supported beams with various kinds of loads. And to have a quick recall to memory, we have noticed or we have taken to understand that the variation of shear force and bending moment happens over the span, and it depends upon the kind of variation depends upon the type of loading. If the loading is concentrated, then variation of shear force over the span of the beam looks like a staircase and it is called a stepped function. While the variation of bending moment is linear, it looks like a straight line. And if the loading is UDL, the variation of shear force is linear and the variation of bending moment will be second degree curve. It becomes parabolic. And as far as concentrated moments are concerned, the variation of shear force, it is not applicable because direct moments have no role to play as far as the development of shear force is concerned, while variation of the shear force bending moment is just like the variation of shear force in case of concentrated loads. That means it is a stepped function. So concentrated loads is to shear force and concentrated moments is to bending moment as far as the nature of variation is concerned. And a very important point to be remembered is, in case of inclined load, only vertical component is to be considered for computing shear force and bending moment. So we will continue by selecting problems over here, which is of a little complexity when compared to the problems that we dealt in tutorial number 2. Here is an example wherein a simply supported beam is loaded with concentrated moments at the extremities at support A and support B. Due to presence of this concentrated moments, the supports will also experience the bending moment, and the magnitude of the bending moment will be equal to the applied concentrated loads. And we know how to create a concentrated moment like this over a beam, over the span of the beam. In fact, we can generate this kind of concentrated moments anywhere over the beam. What we need is we have to weld a frame like this, a vertical frame, and we need to apply a force like this. Or we can have a frame crossing the beam span and we can apply a couple force, that is a force couple, which can create moment. Therefore, it is situation specific. Sometimes a beam must experience, or beam may have to experience concentrated moments like this, and concentrated by all said and done, they are also included under loading category. Therefore, beams can be loaded with concentrated moments rather. So first of all, we will, as a first step, we will calculate the support reaction, and here RA plus RB equal to 0 because there are no vertical forces. And if we take moment with respect to A, and we will have RB into 3 anti-clockwise moment, which is minus, plus 30 the direct clockwise moment, minus 30 the direct anti-clockwise moment acting at support A. Therefore, RB will become 0 because 30 will cancel away, and we will get RB equal to 0. That is reaction at B equal to 0, and therefore reaction at A is also equal to 0 from equation number 1. Therefore, since there are no reactions at A and B, this beam sans shear force. There is no shear force acting on any point over the beam. Therefore, there is no shear force over the entire span of the beam. That means the beam must be subjected to uniform bending moment. Okay, and shear force is 0. Therefore, if at all we need to test a material or test a beam exclusively for bending moment, this is the kind of load. And we have discussed another kind of load in our previous tutorial, and we call it as 2-point loading. There also, over a certain zone of the beam, there was no shear force, and in this zone there was a uniform bending moment, and such a moment is called as pure bending moment. And here we will compute the bending moment now, after having noticed that there is no shear force, and we have to take just to the left of B. Just to the left of B, there is a effect of this concentrated moment concentrated moment, and this concentrated moment will make the beam to hog. Because if there were to be some reaction, this reaction would have caused, let us say at this particular point, would have created anti-clockwise moment, which would have made the bend, which would have made this particular beam to go for sagging. And since this is a clockwise moment, it will make the beam to hog. Therefore, the clockwise moment to the left of this section, just to the left of this section, happens to be hogging in nature. Therefore, it is minus, because it will lift the beam up. Okay. Therefore, the bending moment just to the left of B is the minus 30 kilonewton meter, which is hogging, and the same magnitude continues till here. And we cannot consider just to the left of A. Okay. And therefore, and the same effect will continue till the end. Therefore, it is a uniform distribution with a negative sign, because it generates hogging moment. It is something like bending a scale like this. So here anti-clockwise moment is applied, and here clockwise moment is applied, and the beam hogs, the scale hogs. Therefore, in such case, if we apply a clockwise moment and anti-clockwise moment at either ends, such a beam doesn't need a vertical support, because it is going to stay in equilibrium just by sheer application of the moments. But anyway, it will also subject the beam into pure bending moment. Therefore, pure bending moment is a uniform bending moment always, and where shear force is 0. This is yet another loading pattern that generates pure bending moment. And we will take on to problem number 9, and this is a cumulative numbering. Beam subjected to several moments and concentrated loads. And here we have 2 concentrated moments and 1 concentrated load. The span details are given, and we will first compute the support reaction RA plus RB, and this support reaction equation comes from the fact that sigma Fy equal to 0, algebraic sum of all the vertical forces equal to 0, under the pretext that the beam is in equilibrium. So RA plus RB equal to 40. This is the one vertical load. Then, in order to determine one of the unknowns, we will take moment with respect to A. We will release this particular support. We will apply this particular reaction, and it is RB going up. It will create anti-clockwise moment. So minus RB into 5, moment Rm is 5 up to A, and 30 the applied concentrated load, minus 20 another concentrated load which is anti-clockwise in nature, plus 40 into 2. This span is, this moment Rm is 2. Therefore, 40 into 2, we will get Rb equal to 18 kilonewton. Therefore, if we substitute Rb over here, we will get Ra equal to 40 minus 18, that is 22 kilonewton. So we will start drawing shear force diagram, and we will simultaneously calculate and we will simultaneously plot, so that our understanding will become clear. SF just to the left of B, and if you take a section over here, it's only reaction that would prevail. It is going up, therefore it is positive. Shear force just to the left of B is 18 kilonewton positive, and it is mounted on the positive side of the diagram. And SF just to the right of C is plus 18 once again up to C, and this is the point C. We need to write this point. This is C. Yeah. Just to the right of C is same 18 kilonewton will continue, because there are no other intervening forces, and it is plotted. So it's a uniform shear force. And once again, SF just to the left of C, when we cross this, the 40 will get negated because it is downwards. So 18 minus 40 equal to minus 22. So the diagram goes down, it takes a downward trend, and this is 22. This is 22 kilonewton, this is 18 kilonewton. If you add them together, the entire drop, if you measure the drop here, it is 18 plus 22, it becomes 40. Therefore, the step size is equal to the concentrated load. And the same thing will continue just to the right of A. So therefore, this is the shear force diagram, and here it is negative, and there it is positive. And here it is 18 kilonewton, here it is minus 22 kilonewton. Right, we will start drawing the bending moment diagram. So here we should recall our memory that whenever concentrated moments are involved, we will stop here and we will consider the bending moment just to the right of D to to elude the effect of this concentrated moment, and we will just move just to the left of D to consider the effect of this clockwise moment. So in the melee we will be calculating the bending moment at each and every point over the beam. So predominant points over the beam happens to be A, C, D and B. At D there is a bending moment variation, at C there is a bending moment variation. Okay, and we should get two steps, one here 30 kilonewton meter and one here equal to 20 kilonewton meter. Let us see. Bending moment values. Bending moment at B equal to 0 because there is no ready-made concentrated moment, it's a simple support. Okay, and bending moment is 0, it is plotted over here. Bending moment just to the right of D is we will avoid this concentrated moment. As I said earlier, it is VB, that is 18 into 1, which will make the beam to go up. Therefore it is sagging, it is positive bending moment. So it is plotted because it's a concentrated load. This is the bending moment involving the concentrated load, therefore it is a linear relationship. So bending moment just to the left of D is 18 minus 30 because this is clockwise bending moment which will make the beam to hog. Therefore it is 18 minus 30 minus 12 kilonewton. So that's also plotted. So here this is 18 and this is 12, put together it will become 30 equal to the concentrated moment. BM just to the right of C. We will come here up till here. So now we have to freshly calculate. It is 18 into 3 positive sagging minus 30 due to this particular moment. It becomes 24 kilonewton. So that is connected by straight line. Once again, bending moment just to the left of C, we have to include this effect, and it is 20. It is anti-clockwise. Therefore, it will make the beam to sag up. Okay, it will create sagging effect. Therefore 18 into 3 minus 30, this one, and plus 20, the concentrated moment. Therefore it becomes 44 kilonewton. Therefore there is a rise. So this is from here till here, it is 44, and this is 44 minus 24. 44 minus 24 equal to 20. Therefore this step height is 20. And bending moment at A equal to 0, therefore we will connect it by a straight line. Here we are getting a very important point where bending moment becomes 0. So bending moment is positive here in this triangular portion, negative here, it goes to positive. So from there is a transition of this bending moment value from negative to positive, or if you come from this side, it is positive to negative. This point of crossing where bending moment is 0 is called as point of contraflexion or point of inflection. Okay, contraflexion. It is contraflexion means positive one side, negative other side. Okay, therefore point of contraflexion or point of inflection is noticed. This point is to be located because this point is very important point in the real world experience, because in this portion of the beam hogs because it is negative. In this portion of the beam sags. Therefore we need to adjust the reinforcements, we need to design the reinforcements, because in this region the tension will be at the bottom, and here in this region the tension will be at the top. So that is the effect of bending moment, which will become clear when we take on to bending stresses. Till then we will just keep in our mind that point of contraflexion is very important and it is to be located at any cost. And it can be located by comparing these two similar triangles. Okay, we'll just do that. Okay, this is the bending moment diagram that we have drawn just now, and this point is to be located, and this point I said point of contraflexion. So we will assume that this distance to be x meters. So since the distance from here till here is 2, it becomes 2 minus x. So this distance is 2 minus x, this distance is x, and this height is 24 kilonewton meter and this height is 12 kilonewton meter. This is a special kind of a triangle in bending moment diagram, but anyway the principle of similar triangles can be used in order to locate this. So we will compare these two triangles. X over 24 of the big triangle equal to 2 minus x divided by 12 of the small triangle. So comparing similar triangles, we will get x by 24 equal to 2 minus x by 12, and upon solving we will get x equal to 1.33 meters. So from here till here, the distance up to the point of contraflexure happens to be 1.33 meters. So we'll go to the next problem, wherein we have a piece of UDL. There are two concentrated loads, and by the by, the beam is overhanging beam, single overhanging beam. Let us see how the pattern of bending moment and shear force would be. So reactions we will calculate. RA plus RB equal to 30 plus 20 plus 20 into 3, equivalent concentrated load. So we have written that. So RA plus RB equal to 110 kilonewton. Now we will take moment with respect to A. Moment with respect to A equal to 0, algebraic sum, and we will write RB into phi. This is RB, which will generate anti-clockwise moment, and the span is 3 plus 1 plus 1 phi. So RB into phi, anti-clockwise moment, 20 into 3, okay, 20 into 3, equivalent concentrated load into 1.5, which is clockwise, because equivalent concentrated load will be acting exactly at the center. So that is the moment. It creates clockwise moment about A, plus 30 into 4. This force will create clockwise moment, and 20 into 1.5 plus 1, 2.5 plus 1, 3.5 plus 3, 6.5, and we will get RB equal to 340 divided by 5, 68 kilonewton. Therefore, substituting the value of RB over here, we will get back the value of RA. RA happens to be 42 kilonewton. So now we will move for shear force diagram, SFD. So shear force values. Just to the left of E. We cannot say just to the right of E, because the beam ceases to exist beyond E. Therefore, it is just to the left of E. Shear force just to the left of E equal to minus 20 kilonewton, because it is going down. It is readily plotted. Now, SF just to the right of B till B, the same thing will continue. It is minus 20. And when we take a section just to the left of B, the reaction is included. Just to the left of B, it is minus 20 plus 68. 68 was the reaction over here, is the reaction over here. It will get us 48 kilonewton. That is also plotted. And it will continue up to just to the right of D. And when we say just to the left of D, 30 will be negated, and it becomes 48 minus 30, 18 kilonewtons. Therefore, we can notice a drop, and this height is 18 kilonewton. And this 18 kilonewton will continue up to C. SF at C is 18 kilonewton, and SF at A we will compute just to the right of A, that is over here up to C. It was 18 kilonewton. Once again, minus 20 into 3. That is equivalent concentrated load owing to UDL. So we will get minus 42 kilonewton as the shear force at this particular point, and here 42 kilonewton happens to be the reaction at A. So reaction at A is positive because it is going up, and we are getting the shear force to be negative. Therefore, the computation of shear force is correct, and the variation is linear. And here we get an important point once again, where shear force crosses its sign. And there is no nomenclature associated with this zero shear force point, but anyway it is to be located. Because wherever shear force, we will later point of time we will prove that wherever shear force is zero, the bending moment is going to be maximum. Therefore, we need to locate this particular point. We will consider this distance to be x, and this will become 3 minus x, and we have two similar triangles, one big triangle and one small triangle. We will do a comparison, and we will get back as to what is the distance of the point at which shear force is 0 from the left support. Okay, this is plotted neatly. This is x, and this is 3 minus x. Now once again we will take on to the different slide for the sake of clarity. Yeah, E is to be located because E happens to be very important point. We'll see that why it is important, okay, when we start computing bending moment. So x and 3x, so x over 42 equal to 3 minus x over 18, because this side is 18. Okay, this is the big triangle, shear force triangle, and this is a small triangle, and they are similar. So point E is to be located. Comparing similar triangles, x by 42, x by 42 equal to 3 minus x by 18, and we will get 18x equal to, and upon solving this we will get x equal to 126 by 60, that is 2.1 meter. So from the left support, the point of zero shear force is located at a distance of 2.1 meters. Now we will start drawing bending moment diagram, and we should not forget to note this particular point, important point, which has arrived just because the shear force was 0 over here. Okay, it's a very significant point. Let us see about its significance. BM at B equal to 20 into 1.5. It will make the beam to hog downwards, therefore it is negative. 20 into 1.5 minus 30 kilonewton meter. Okay, it is negative, it is plotted already, and we need to connect them by a straight line. Then BM at D equal to minus 20 into 2.5, 1.5 plus 1, 2.5 plus 68, that is a reaction into 1 meter. 1 meter. Reaction is 1 meter. This is okay. We will just remove this. Yeah, and when we simplify this, we will get bending moment at D to be positive, and it is 80 kilonewton per 80 newton meter, 80 kilonewton meter actually, and this is to be connected by a straight line. Yes, that is also done. And bending moment at C, we can come from this side. While calculating bending moment at C, we can come from this side. So 42 into 3, which is positive because it will lift the beam up, creating sagging, minus 20 into 3, equivalent concentrated load, and the moment arm. Moment arm will be exactly at the center. The equivalent concentrated load will be at the center. Therefore, the moment arm will be 3 by 2, that is 1.5. So 42 into 3. So whenever we move over the beam, this is a very important point. Okay, we need not have to come from this side. Okay, so avoiding drudgery, we can come from the left side. Okay, so 42 into 3 due to this reaction, minus 20 into 3 into 1.5, the negative bending moment due to applied load, that is UDL. So it becomes 36 kilonewton meter. So here it is 36 kilonewton meter. It is, and here we will calculate. It is at a distance of 2.1 meter. Just now we have located the place of shear force becoming 0. Okay, it is at a distance of 2.1 meters from the left support. So it is 42 into 2.1. Okay, reaction into 2.1, which is sagging, minus 20 due to UDL acting over the portion of 2.1 meter. Okay, and a span of 2.1 meter. It is 20 into 2.1 into 2.1 by 2. Okay, it will be at the center once again at the half of 2.1. Okay, therefore this is also multiplied as a moment arm. We got 44.1, just higher than 36 kilonewton meter. Therefore the point goes over here, and bending moment at A equal to 0 because it is a simple support. Now we need to, since this region is covered by UDL, it should be connected by means of a parabola. Of course, this should be the straight line. This should be the straight line. From here till here, it should be straight line. It is not a parabola. It looks like parabola. It's a straight line. Okay, kindly make it straight. This is a straight line, and here exactly parabola will start, and this height is 36 kilonewton meter from here till here, and this height is 44.1 kilonewton per meter. So very interesting point here we learned is, wherever bending shear force is 0, the bending moment is going to be maximum, and wherever shear force bending moment is 0, it need not be, the shear force need not be maximum. The converse is not true. But wherever shear force is going to be 0, there we will get either positive bending moment to be maximum or negative bending moment to be maximum. Okay, that is a very important learning. So therefore the points of 0 shear force is to be necessarily located. They should be necessarily located. Point of contraflexure is to be located again. That can be done by comparing similar triangles. We will consider this distance to be x, and the other distance will be 1 minus x, and we know this ordinate. It is 30 kilonewton meter. This ordinate we know, just below this particular load. This ordinate we know, I mean it is 30 kilonewton meter, 30 kilonewton meter, and this is 18 kilonewton meter. Therefore we can compare the similar triangles by assuming this distance to be x, and we will just do this for the sake of clarity. And this is straight line once again. This should be corrected. It should be made straight line. It is not a part of the parabola. Okay, parabola starts from over here. Therefore we will compare the similar triangles. X over 30 equal to 1 minus x over 18. This is 18. The other ordinate, positive ordinate, the positive ordinate over here, from here till here, is 18. Therefore we will make use of this similarity in these two triangles, and we will compute x value. X value happens to be, upon solving, 0.625 meter. So with this we have completed the bending moment and shear force for relatively typical problems. It's not complex problems. So in the next tutorial we will discuss some of the complex problems in bending moment and shear force category, and we will also come out with a relationship between shear force and the loading intensity and bending moment and shear force. Until then, bye, and if you have liked this video, kindly subscribe to my channel, and thank you.